Zurita from Group K. So our project topic is sentiment analysis with a domain shift. What is sentiment analysis? Sentiment analysis is the process of automatically classifying text as positive, negative, or neutral using a machine learning model. For example, great service is positive, worst experience ever is negative, flight departs at 6 p.m. is neutral. So we have different reward applications, for example, customer feedback analysis, social media monitoring, academic research, and student communication tools. So we have our problem. The problem is domain shift. Now, this is the core problem our project tackles. We trained our model entirely on Twitter data and we tested it on different platforms. That is Gmail, WhatsApp, app reviews. So this creates and this creates domain shift. And domain shift is when a model trained on a type of text is tested on a different type and its performance drops. So we have a key challenge whereby Twitter language has slangs, hashtags, airline names, and this is completely meaningless in Gmail and WhatsApp. So our data, we have training data and test data. The sources of our data sets, for example, tweet was got from Cargo. All of the training sources, all of the training data were got from Cargo. So we have Twitter data set and SafeNet data set. Those are the different rows. And this data set we have Gmail, WhatsApp, app reviews. Those are the sources, student emails, student group chats, Google Play Store, and those are the different samples objectives. For example, build the classifier. Here we built a sentiment analysis model trained on only Twitter data. Here we tested our model on entire different data set from Gmail, WhatsApp, and Google Play Store. We measured the domain, we measured the domain shift, how much the accuracy drops across the domains. So we have mitigate shifts using stacking examples, glove embeddings, engineered features, and pseudo labeling.
My name is Kaswale Taufik Larry, and I'm going to take you through the data and pre-processing part. So to begin with, we use three training data sets, that is the airline sentiment, the Twitter sentiment, and the tweets. And with these are the number of rows that each data set had. One of the problems that was aligned was that each data set used different names, that is the airline sentiment and the sentiment beginning with the capital A's. So with this, there was a label unification challenge. To solve this, we used three consistent class labels, that is the positive, the negative. And this wasn't the only challenge that we faced, or that was with the data. The other challenge during cleaning was, as stated, each data set using different naming and was solved by custom mapping function of positive, negative, and the neutral. Then we go to the missing text that was also viewed in the data. Some rows had empty or null text fields, of which we dropped these with the missing values. Then for the duplicates, which was also another problem, identical tweets appeared multiple times across the data sets. We duplicated on content. Then the classing balance, of which the negative class heavily outnumbered positive and the neutral class, of which we removed about 5,000 negative samples to rebalance the classes. This was the kind of the data before balancing, which the negative class was really higher, or it had more of the data compared to the other two classes, the neutral and the positive. And this was after the balancing was done of the 5,000 samples. Then we come to the source contribution. The source contribution here shows of how each data set contributed. The Twitter data set really contributed more of the final data set that we are going to use, followed by the airline tweets, and then the social media as well, which really contributed less of the data. So these are some of the words that the model considered: positive, negative, and neutral.
My name is Muhindo Juliana, and I'll be taking you through the next slides. So we noticed that raw text alone isn't enough, and therefore we went beyond words and extracted 12 metadata features that capture how people write and not just what they write. For example, lots of caps means emphasis or anger. Many exclamation marks could mean excitement. Question marks could signal confusion. We also detect words, academic words like exam, platform names like GitHub, or even emojis. All these things count because WhatsApp messages are very different from Gmail. So these two features give our models extra human-like clues. Okay. Now, how does a machine understand words? We use GLOVE embeddings, where each word becomes a 100-dimensional vector pre-trained on billions of sentences, so that words like failed, words like stressed are already understood as similar even before training humans. So we then built 10 models across 4 levels. For example, on classical, we had naive-Bayes logistic regression, SVM, and across neutral, we had MLP. For deep learning, we had LSTM, BiLSTM, CNN, LSTM, and GRU, and a transformer which was DistillBat. So each model sees the same data but then learns differently. So why did we train 10 models? It's because no single model is perfect, but together they are powerful, okay? So we use stacking, where all the 10 models make predictions, and those predictions become the input to the XGBoost meta learner, which learns how these models work and which one to trust. So think of it as 10 experts voting, okay? And XGBoost is the judge who decides whose opinion matters most. So all this ensemble, all this stack drives our final sentiment output.
My name is Nasuna Ivy, and I'm talking about how well we did on Twitter. As you can see, our mean OOF accuracy is 88.27% out of the fold cross validation score. And these are out of modules out of the 10. Yeah. So now this is the bar chart indicating the individual accuracy for the 10 different modules used. As you can see, these two batches on top, followed by deep learning modules in the middle, followed by our classic methods that are trailing slightly. Our classical methods didn't perform so well. But no module is perfect. That's the exact argument of stacking them together. So as you can see, accuracy drops when we move from Twitter to unseen student platforms. As Twitter, you can see Twitter has 88.27%, but when we move to other platforms like WhatsApp, app reviews, and Gmail, it dropped. For WhatsApp, it's 60. For app reviews, it's 54%, and for Gmail, it's 50. Yeah. So the accuracy reduced slightly when we went to new data. Now, this may look like a failure, but measuring this drop was honestly our core objective. This is the domain shift made visible. The module went from 88% to between 60 and 50. Yes. And our aim was mainly to keeping this gap as small as possible. Now we look at the F1 scores. Looking beyond overall accuracy, the F1 scores tell a more specific story. A negative sentiment was more reliable and detectable, as you can see. Neutral and positive didn't perform so well, but for the app reviews performed, but the neutral class didn't do so well. Now we go to our WhatsApp confusion matrix. Our WhatsApp confusion matrix indicates that the negative column was relatively clean and the module got those right. But looking at the positive and the neutral, there's a clear confusion between them. A student typing, fine, see you tomorrow, does not carry the same energy as a positive tweet. So the module couldn't figure that one out. Those are the results for this for understanding why the module made the decisions it made. Thank you.
Good afternoon, madam. I'm by the name of Tagola Mungwa David, and I'm going to be talking about the Shapley additive explanation. So this is just a chart that shows the different features that the model used to make the predictions. So you can see that BAT is at the top, random forest, long short-term memory. This means that whatever these models said is what our meta learner, which was the XGBoost, would go with. And then you can see that the technical success, which was an engineered feature, also contributed slightly to the model prediction. So the next thing I'm going to talk about is the local interpretable model agonistic explanation. So this one just tells us why our message was labeled the way it was labeled. So the message we are dealing with is the cell deployment to production failed check log. So The word failed contributed most, followed by check, followed by production, followed by, whereby logs, deployment, and Vercel did not contribute anything. So the next thing I'm going to talk about is the ROC curve. So this ROC curve just tells us how confident are our models in determining the different classes we have. So the closer your value is to 1, the better. So you can see that the positive is closer to 1, followed by negative, and then the neutral. So in conclusion, we fought against that domain shift by using the ensemble, which was the XGBoost, and then the different models that I talked about by the previous speakers that we had, and then engineering features using love embeddings and then pseudo labeling. Yeah, thank you, madam.